Okay, so in this lecture I am going to talk about optimum demodulation for digitally modulated signals. Um, Actually, we have very well developed theoretical tools available to study the subject of optimum demodulation. Okay, so these theoretical tools are studied typically in advanced courses like in your master course, especially when you are taking PG courses in communication systems or signal processing. Then definitely you'll be studying this course called detection and estimation theory, or simply called detection theory, and sometimes mathematicians would like to call statistical hypothesis testing. So therefore you can study under the topic of let me okay, so detection theory or statistical hypothesis testing theories. So this is little advanced courses, and when using this course you can develop the model, or you can design the optimum demodulator using this subject. Now we know that in digital communication you have the transmitter, and you transmit certain waveforms or pulse shapes to the channel, right? And here you have the receiver, and let's say you are using M array modulator at the transmitter. M array modulator means you have capital M number of waveforms. Let me call S0 of t, S1 of t, and up to capital S sub M minus 1 of t. So therefore I have M number of waveforms. You choose any one waveform and transmit to the channel, and the channel, from the channel the receiver receives the waveform. For timing, let's say the noise equal to 0. Okay, if noise equal to 0, then the receiver will transmit whatever the waveforms you are transmitting. Therefore, in every interval of interest, because in digital communication we divide into interval, like let me call this a symbol interval or bit intervals. This is symbol interval, or you can call bit interval. Fine. Now every bit interval, or every symbol interval, you are transmitting different pulse shapes or different signals. So therefore the received waveform in the absence of noise would be one of the many possible set of waveforms which were defined by the transmitter or defined by the modulator. So the modulator will define these waveforms. For example, like for example, here I considered a M array modulation scheme. Then you have dictionary of M possible waveforms. So these are called dictionary of M possible waveforms. Dictionary of capital M possible waveforms. Okay, M waveforms. Therefore, if you transmit any one wave, let's say you are transmitting S0 of t, here you are transmitting S sub M minus 1 of t, and here you are transmitting S3 of t, and so on and so forth. The same thing you will receive here. If there is no noise, then the same waveform, but that waveform is attenuated, that's all. So the waveform you will get here also you are going to get S0 of t, here S sub M minus 1 of t, and here S3 of t, and so on. But the life is not like that. So what happens in real, whatever you transmit, whatever the signals are transmitted by the transmitter, then in the channel noise will come and add with the input signal, transmitted signal. Therefore at the receiver you have the signal plus noise will occur. Okay, so one of this waveform is received in the presence of noise, and in that case a typical hypothesis testing approach to this problem will ask which of the M waveforms was most probably transmitted, okay, based on the received waveform that you have got. See, you are transmitting the signal, and that signal is contaminated by the noise. Let's say you are transmitting a pulse A times S of t. Let's say you have a pulse. This is my pulse, basic pulse shape, and the amplitude is A. Now if you transmit over the channel, if there is no noise, you will receive the signal like this. Maybe let me draw properly. Maybe you'll get the pulse like this, attenuated pulse. Attenuated pulse. If no noise. Suppose you transmit the same pulse with a noisy channel, then what happens, you will receive the attenuated signal, and also it is come something distorted signal. So the signal will be like this, attenuated as well as distorted signal. Therefore your pulse is contaminated by noise. Therefore we don't know which pulse was transmitted. That is secondary actually. First of all, we need to know whether the received signal contains either pulse plus noise or noise alone. Therefore at the receiver we have one very big question, that is the received signal, let's say R of t, contains signal plus noise or noise alone. That's what we want to consider. Therefore the hypothesis testing approach to this problem will ask which of the m waveforms was most probably transmitted based on the received waveform. This is my received waveform that you have got it. So given a particular waveform that you have in a particular interval, which of the m hypothesis is true? That means whether the first waveform is true, or second waveform is true, or the third waveform is true, or second waveform is true, or the mth waveform is true, capital M. I'm going a little slowly because this is very important topic in digital communication, so that's why. So this is a subject which is studied under these titles: detection theory and or statistical hypothesis testing. So to take that approach, one has to go through a bit of formal background, for which we don't have time, and moreover it is a full-fledged one semester course, okay, and it's a little difficult to cover in this digital communication course, okay. So therefore what we do is we will take really a simple and slightly more simplistic approach which embodies some of the very basic result that we got from the detection and estimation theory. So which we will try to motivate. So therefore we will try to motivate both mathematically as well as intuitively. Therefore I am planning to take a slightly more simple and slightly ad hoc approach, but still but it will still be quite satisfactory. So the most basic principle that finally comes out of this detection and estimation theory is quite simple and concise. Essentially it is the principle of matched filtering. So matched filtering, okay, this concept is derived from detection theory. It is a result of your detection theory. So instead of taking the formal course and analyzing rigorously through theoretical tools, and finally you'll end up with something that is called principle of matched filtering or matched filtering concept. So we will take the result and we'll try to motivate intuitively. I'll try to motivate intuitively. So the result is very quite simple and concise. So this matched filtering provides no answer to many of the demodulations, many wide variety of demodulation schemes, digital modulator waveforms. So if you study the basic principle of the matched filtering, then we will be able to answer for many digitally modulated signals. So therefore, once we have thorough knowledge in matched filtering, then we will be equipped to study optimum demodulation for digital modulations. To complete the statement, as I already said, we will primarily be looking at optimum demodulation in the presence of noise. So we are going to consider only noise. As I say, mentioned one of my previous lecture, that there are many impairments which will contaminate the noise. So mainly noise, then interference and distortions. But in this lecture, no, I am going to consider only noise. I am not going to consider no interference or distortion. So, but one could pose the problems of optimum demodulation in the presence of noise, distortion and interference and all these things. But obviously this problem will become more complex to study at a time, at least in this stage. Therefore, to make our life simple and to study easily, so we are going to consider only noise. Okay, so therefore noise alone will be considered. considered in this course. Consider. It is usually simpler to study them in a systematic step-by-step manner. You first include noise and try to demodulate the noisy version of the signal, and then introduce distortion and study the character of the system, and demodulate the signal at the output at the receiver, and then include interference, and then see. So you have to go step-by-step method. At one shot, you should not include all these three impairments together and try to do the demodulation. Then it will be very complex. So don't do that. Okay, so one assumption that we'll make here, so I'm going to make many assumptions. Okay, the first assumption is I'm going to consider only noise, and the second assumption I'm going to consider is like the channel introduces only noise. Channel introduces only noise. In fact, the channel introduces distortion also, but that I'm not going to consider. So it is not doing anything funny except adding noise, and this noise also added additive nature. So that is why this is called the additive white Gaussian noise, AWG in short, people will call it. That we'll see later. So it has a sufficient bandwidth. The third assumption is it should have sufficient bandwidth. The channel should have. Channel has, or I can say channels have sufficient bandwidth. If it doesn't have sufficient bandwidth, then what will happen? The signal will be distorted. Okay, so we are assuming that the channel has channels have sufficiently bandwidth. That means what? It produces faithfully except for the noise. Therefore, we can do a demodulation of a waveform one symbol at a time. So no impairment. The fourth assumption is no impairment, no other impairment, no channel impairment. That is distortion. No channel impairments. And fifth assumption is no interference from one interval to next interval. No interference from one interval or one symbol interval to next symbol interval. Next symbol interval. Okay, so and no cross interference from other channel. No cross interference from other channel. Meaning, suppose when I say no interference from one interval to next interval, that means you have a pulse in this interval. This is, let's say, T1, and the next interval T2, and the next interval T3. So what you do, you take a no pulse like this. If you take Fourier transform, then you'll get a sync pulse like this. Therefore, this pulse will not die out quickly, and this pulse will interfere with the second symbol. So therefore, the first symbol will come and interfere the second symbol, and sometimes the first symbol may have enough to interfere the third symbol, and the second will come and interfere the third one. So like that, these are called inter-symbol interference. There is an interference between one symbol to another symbol. And another one is no cross interference from other channels. See, you have one channel, one pair of channel. You have transmitter 1 and receiver 1, and you have transmitter 2 and receiver 2. There is one more system, two digital communication systems. Okay, let's say the second system is operating in the neighborhood of the first system. So therefore, what will happen? So the second system will come and interfere the first system. So that is called cross interference from the other channel. Therefore, in our study, we are assuming that no cross interference from other channel, no interference from one interval to the next symbol interval, no channel impairments. That means no distortion, and the channel has sufficient bandwidth. That means it can faithfully reproduce the pulse at the output, and channel introduce only noise, and that noise also additive noise. Okay, so these are the few assumptions that we consider in demodulation process. And the last very important assumption is we are going to study symbol by symbol approach. Okay, first you take one symbol, finish it, demodulate it, and decide it what was transmitted and then go to the next symbol. So this is called a symbol by symbol approach. Symbol by symbol approach. Okay, so the important assumption is that we have made here is that we have a perfect timing synchronization. To do this symbol by symbol approach, I should know where the pulse is starting and where the pulse is ending. Okay, I should know the symbol duration perfectly. So that means I need perfect timing synchronization. So this needs a perfect timing synchronization. Perfect timing synchronization between the transmitter and receiver. So the problem is considerably simplified if you make these assumptions. Okay, so we are taking this kind of assumptions. Because of that, the problem will be very simple. Because all we are looking at is one symbol interval at a time. So given one symbol interval, we know we are likely to get one of several possible waveforms. See, I have several waveforms, right? S naught of t. Dictionary of waveforms, that's what I said, S2 and up to S sub m minus 1 of t. So dictionary of m waveforms, out of this m waveforms I may get one waveform in a given interval, a given symbol interval. So we are likely to get one of several possible waveforms and we like to obtain some method for deciding which was transmitted. So therefore further we are simplifying the problem by just to look at much simpler problem of detection of the presence of a signal in a given interest. So what I am saying is, let us look at the nth observation interval and whether it has a signal or it may have only noise. So the problem is you have many intervals and look at nth interval. In the nth interval, just to observe here. And in this interval, whether it has signal plus noise or noise alone. And once if you say signal or noise, then once if you say no signal alone, then you can later on think, okay, if it is signal, then which signal was transmitted. So the first thing is I should know whether the signal exists or not. Okay, if signal exists, then the next my job is I need to know which waveform was transmitted, because I have m waveforms. Out of this m waveforms, which waveform was transmitted, that's what I need to look at. Therefore the first thing is the presence or absence of the signal. So let us try to find a method by which we can detect the presence or absence of a signal. So that is the first thing. So detect the presence or absence of the signal. And the second is then find which signal was transmitted. Then the second is presence of S naught of t or S1 of t or S2 of t or Sm minus 1 of t. The first thing is detect whether the presence or absence of the signal. Absence means it contains only purely noise, nothing can be done in that. Okay, therefore the first step is detect the presence or absence of the signal, and the second stage is presence of S naught of t or S1 of t or anything, presence of this or that, which one. So therefore to start with, let's look at the detection of simply presence or absence of the signal in a particular observation interval. It is a much simpler problem now to look at. So that brings us really to the concept of matched filter. So to look at whether the signal is present or absent, that is done with the help of a device called a matched filter. So the matched filter will tell you whether the signal present or not. That is presence or absence. That can be done with the help of matched filter. In fact, the matched filter is designed from the result that we got from your detection theory. Okay, and then this is one part. Now let us look about signal, how a signal is modeled. Now at the transmitter I am transmitting a signal, and the transmitting signal is nothing but it's a pulse. Okay, some kind of square pulse, as I said, or you can half cosinusoidal pulses or half half sinusoidal pulses like this, and the pulse has certain amplitude A. Therefore, the basic pulse shape is S of t. This is my basic pulse shape, and the amplitude of the pulse is A amplitude. Therefore, my transmitted pulse is A times S of t. This is the transmitted pulse. Okay, and which is of finite energy pulse. Let us assume this is finite energy pulse. Okay, with energy EP, and this A is the scaling factor. A is the scaling factor. Now, how do you find the energy? Your energy EP equal to integrate A times S of t and take square of this, take modulus and square of this, and integrate from minus infinity plus infinity. It is in the time domain. Okay, the similar expression you can get in the frequency domain also by using Parseval's theorem, like integral of A times capital S of F times df modulus and square df and minus infinity plus infinity. And moreover, in the previous lectures I already told you, like it is very easy to represent the signal in the baseband complex notation. Therefore, we are going to represent this pulse shape like it has a real part and the quadrature part, that is imaginary part, and this is very useful to represent. Okay, so we can represent our various kinds of modulation schemes very conveniently using complex notation. So in general, we will permit this pulse shape to be complex. The pulse can be in complex. So it has a real part, that is in phase component, and imaginary component Si of t. So we will try to use this complex notation. So this pulse is received at the receiver and contaminated by noise. Okay, so now let us try to model the noise. How do we model the noise? So the noise also again think in terms of real part and imaginary part in the complex baseband notation, and the first assumption that we are going to assume is it is a wide sense stationary or covariance stationary. That means the covariance function depends only on the tau, and it does not depend on the absolute time where you are taking the sample from the random processes. So I have put a separate lecture for this noise. You can go through that. So let me not discuss about noise in this particular lecture. Okay, please go through that noise separately in some other lecture. So that is there in the playlist, you can look at. Now let us enter into the detection problem. So how we can model the detection problem. Okay, so as I said, our immediate problem of interest is relatively simpler one, because we have made so many assumptions, like 6-7 assumptions. So we will try to evaluate a strategy to detect whether a received signal, let me denote received signal V of t, received signal, which is a noisy version of the transmitted pulse. So your transmitted pulse is A into S of t. This is your transmitted pulse. So the received pulse is a noisy version of the transmitted pulse, A times S of t plus some noise. Or sometimes you'll get only noise alone. Okay, it contains only noise. Sometimes it can have only noise. Okay, so let me denote this noise by N of t. And okay, so we are really doing a hypothesis testing here with two possible hypotheses. So let me call hypothesis H1, that is V of t is a noisy version of the received pulse, A times S of t plus noise N of t, and hypothesis H2 is V of t is equal to only noise. So these are the two hypotheses. So under hypothesis H1, we are saying that our received signal, which we are denoting V of t, consists of the transmitted pulse A times S of t plus the noise N of t. Now under the hypothesis H2, what we are saying is the received signal V of t consists only of noise. So in front of us we have two hypotheses, and we need to say which hypothesis is true. Okay, so therefore let me write down in mathematically in terms of words. Detect whether a received signal V of t consists of a pulse in noise or noise alone. Okay, so these are the two hypotheses that is there in front of us. So the question is, which of this is true? So all we have with us is observed waveform. So we have V of t. What is V of t? The received waveform or observed waveform. So from the observed waveform, I should say which waveform is true, which hypothesis is true. So we want to go from this observed waveform over some interval. Maybe you are observing this interval. Interval by interval you are observing and making a decision. Now at least at the moment let us not worrying about which specific interval. Let's take one interval, any arbitrary interval. So therefore we are talking of the section of the single pulse occurring somewhere in the simple interval. So all we have is this V of t and we need to process it. So this V of t, first we process it, and after the process finally produce a decision. What decision you have to take? That decision says whether hypothesis H1 is true or H2 is true. So the decision is H1 is true or H2 is true. If H1 is true, then I can think which waveform is present. Therefore I have S1 of t, S0 of t, S1 of t up to S sub m minus 1 of t. If it is not true, then H2 is true, then I can decide that no, there is no signal and it is only noise. Then I can discard that particular symbol interval. Therefore first you decide or take a decision that from whether take a decision from the observed waveform that the signal is present or not. If it is not, okay, leave it, it is completely noise. If it is present, then you have to take which waveform was transmitted out of this m possible waveforms, dictionary of m possible waveforms. Okay, and if you go by this process, this entire process is called a non-structural approach. Non-structural approach. Okay. So therefore in non-structural approach, generally what we do is we will start the problem theoretically and we will find the solution, and the solution will itself tell you what is the structure of it, what kind of structure, that means what type of electronic circuits you wanted to implement this. See, after all, theoretically what we do, we will work on it and finally we will arrive with some kind of an equation or some solution, and for that solution, for that equation, you try to implement in hardware. So in the hardware sense, either you want to design this filter or that filter or this circuit or that circuit, whatever it is. Therefore you start the problem and then find the solution, and that solution will itself tell you what the structure is and what is the processing that we have to do. Therefore what is the structure of the processor that one has to finally adopt. Therefore in non-structural approach, so this is the systematic way people will do. So you take this theoretical tool and do step by step, and finally you'll end up with a solution, and with that solution you will implement the structure, or maybe a low pass filter or high pass filter or sampler or whatever it is. I don't know what is going to be. Okay, but this is a non-structural approach, but this non-structural approach is little lengthy and we don't have enough knowledge in this, at least in this course. So you'll be studying this course in your higher classes, like in your PG, especially in communication systems, Master of Engineering in Communication Systems, or Master of Engineering in Signal Processing. Okay, so because we are not really equipped with the tools of such a typical hypothesis testing tools, theories, or detection theory, what we will do is we will have to take the structural approach. So in this course we will take a simplified version of non-structural approach, that is called a structural approach. You will study this course in your PG class, non-structural approach, in detection and estimation theory or hypothesis testing theories. But in our course in digital communication, we are going to follow this structural approach. And the structural approach, starts by saying something that about what kind of processing we need to carry out. So the structural approach is nothing but your matched filter. Okay, so this is very simplistic approach, and still it will it will give the quite satisfactory result. So in the next lecture I will start this matched filter. So at this point let me stop. Before this, let me summarize the points that we discussed. So this is a very important lecture. So we are in the business of optimum demodulation. For optimum demodulation, we need some some math theoretical tools, and the theoretical tools are studied under the titles of detection theory or statistical hypothesis testing. Like in digital communication, you have transmitter and receiver. In the transmitter, you have dictionary of m possible waveforms, and any one waveform you are transmitting to the receiver. And now in every symbol interval you are transmitting different waveforms, and at the receiver, if there is no noise, then your demodulator job is very easy. Okay, because your signal is only attenuated, so it's very easy to identify which pulse or which signal was transmitted. But in reality, that is not the case. The life is not that much simple. So therefore what you need to do is you need to work on it, how your when your signal is contaminated by noise. In that case, how do you do the demodulations? Because when the noise enters with the signal is attenuated first and also disturbed by your noise. Therefore, you'll get a noisy signal or noisy pulse. In that case, how to demodulate? So to do that, we are making some assumptions. Okay, so what are the assumptions? First, we are going to consider only noise, no interference, no distortion. Okay, noise alone will be considered, and this noise also not multiplicative noise, it is additive noise. The noise is adding with the your transmitted pulse or transmitted waveforms. And the channel has sufficient bandwidth and no channel impairment, and no interference from one symbol interval to the next symbol interval. One symbol, whatever the pulse you are transmitting at one symbol interval, that will not go and disturb the next symbol interval, and no cross interference from other channels. These are the assumptions we consider, and we are going to follow this symbol by symbol approach. You do the demodulation at one particular symbol interval and finish it, and then go to the next symbol interval. So for that, we need to have perfect synchronization, where the bit starts and where the bit ends, and the duration of the your symbol interval. This all informations we should know between the transmitter and the receiver. That means what? Your transmitter and the receiver both are perfectly synchronized. Okay, and then the detection problem is posed as like detect the presence or absence of the signal. First, we should know whether the signal present or absent. Once you say it is absent, then leave it, discard it. Okay, go to the next interval, next symbol interval or bit interval. But if there is a signal present, then we have to think which signal was transmitted, because you are not going to transmit only one signal for all the time. Okay, every symbol interval you are transmitting out of m possible waveforms. So you could have transmitted many waveforms, capital M number of waveforms if you take m array modulations. Therefore, out of these m waveforms, which waveform could have been transmitted, that we need to find out. That is the second step. So in the demodulation process, the first step is we need to know whether the signal present or absent. So we need to detect the presence or absence of the signal, first step. And second step is decide which waveform was transmitted. That is the second step. So to detect the presence or absence of the signal, we are going to use something called matched filter. So in then after that we said like at the transmitter we have signal, and in the channel noise is adding. So therefore we have two components, signal and noise. And the signal, how do you say? We have the basic pulse s of t, and the basic pulse has certain amplitude a, that is a scaling factor, and you are transmitting this pulse a times s of t, and we assume that this s of t has finite energy. So it is a finite energy pulse, and the energy of the pulse can be calculated using this formula in the time domain as well as in the frequency domain using Parseval's theorem. This is the relation between time domain and frequency domain. And we already discussed that it is very convenient to represent these waveforms in the baseband complex domain. Therefore, my basic pulse can be represented in terms of the real part and the imaginary part in the complex representation. And then noise also we assume that it is a WSS noise, weakly sensed stationary noise or covariant stationary noise. And this is noise is little no big topic, so I have discussed this noise separately in another lecture. Please go through that. So next we will enter into detection problem. So the detection problem is as follows. So you have the received signal V of t. That received signal is like a noisy version of your transmitted pulse or noise alone. So sorry, we have two hypotheses, H1 and H2. So we need to come up whether H1 is true or H2 is true. If H1 is true, we know what to do. H2 is true, we know what to do. If H1 is true, the first you have to detect, okay, first observe the waveform and process it. Then after you take a decision whether H1 is true or H2 is true. If H1 is true, which are the waveforms could have been transmitted. So this approach is called a non-structural approach, and at this stage we cannot use non-structural approach in our UG class, especially in digital communication. It is a full-fledged course, detection and estimation theory. In a semester, it is a full semester course, separate course. Therefore, what we do is we will try to adopt a separate approach that is called structural approach. So your matched filter is an example, the best example of your structural approach that we will discuss in the next lecture. Okay, thank you very much.